Okay, so today we're going deep, really deep, into something that kind of sits right on the edge of what we even know about, well, reality itself.
You got it. Space-time singularities and, of course, those ever so popular black holes.
Yeah, if you're listening to this, you're probably like us, right?
Yeah.
You like to think about the big questions, existence, what it all means, the universe, all
That's
that jazz.
right. It might sound like, oh, this is just physics, right? Equations and whatnot.
But trust me, there's like layers and layers of philosophical head scratchers here. It's deep, man. And we're using, a pretty solid guidebook for this one, the Stanford Encyclopedia of Philosophy.
Yeah, no better place to grapple with these mind-bending concepts, I'd say.
So before we get too far, I gotta admit, it's kind of wild how few philosophers have actually like really dug into these topics. The source even calls it like a wide open field for exploration.
Yeah, that struck me too. I mean, we're talking about stuff that challenges like our most basic intuitions about space and time, even matter itself.
Mm.
And yet, the philosophy world has been, I don't know, a bit hesitant to jump in.
Maybe they're just waiting for the physics folks to like figure it all out first.
Could be. But look, getting into this stuff does require, some familiarity with the whole general relativity framework.
Hmm.
Our source even recommends checking out the beginner's guide in the SAP entry on the whole argument if you need a refresher.
Yeah, good call. But the payoff is like huge, philosophically speaking. We're going to come out of this with a much richer understanding of some of the most, well, extreme and mind-boggling aspects of the universe. So that's our mission, really, to unpack the philosophical puzzles that come with singularities and black holes. What are these things? Do they even exist? And what does their existence, or maybe non-existence, tell us about reality, like at the most fundamental level?
Exactly. Big question. So where do we even begin? Let's start with singularities. What happens when we say, okay, there's a singularity?
Uh-huh.
What are we saying is breaking down?
Okay, breakdown, I like that. So I guess the starting point is that everyone kind of agrees, right?
Yeah.
Einstein's theory of general relativity allows for the possibility of singularities.
Right, but the moment you try to actually define what a singularity is, like precisely define it, the consensus kind of falls apart,
Hmm.
you know?
Ah, okay, the cracks start to show.
The real problem, the thing that really makes this a philosophical headache, is that singularities seem to represent like a breakdown of the very geometry of space-time itself.
Oh, okay. That's where things get weird, right? Like, if the very geometry of space and time is collapsing, how can we even talk about a location, a point where this happens? It's almost like trying to pinpoint the location of, I don't know, nothingness.
Precisely, and that's why some argue that instead of thinking about these distinct singularities, these points, we should really be talking about singular spacetimes as a whole. It's the entire spacetime structure that's becoming, well, singular.
Got it. So kind of like shifting the focus from a pinpoint to the whole canvas, right?
Exactly. And for our purposes today, we'll mostly use those terms interchangeably, but it's a super important distinction for any serious philosophical analysis. But the history of how we even got here, how we define these things, is a whole other rabbit hole. The most popular definition used by physicists relies on this concept of path incompleteness.
Path incompleteness. Okay, for someone like me who's more into the philosophy side, what does that even mean? Break it down.
Imagine you have a particle, right? And it's cruising through space-time. We can map its journey as a path. Now, if that path has a finite length, in terms of the particle's own experience of time, what we call proper time, but it can't be extended any further, like it just stops abruptly. That's path incompleteness. It's like the universe is saying, nope, that's it for this path, end of the line.
Whoa. So it's not hitting some wall, not running into a force field. The path just stops. That's messed up, metaphysically speaking.
It is. And it gets even weirder. There's this attempt to formalize this using something called generalized affine length. But its physical meaning can be kind of opaque. There's this example, Girash's spacetime, where all the paths of freely falling particles are perfectly complete, but if you have an accelerating particle, its path can still end abruptly. And the generalized affine lengths for these paths can actually be infinite, which would seem to imply no singularity, according to that definition. It's like the math isn't quite capturing what we intuitively think of as a breakdown.
Okay, so we need a definition that makes more sense physically, experientially. So that leads us to Manchak's idea of, what was it? Effective completeness.
Bingo. Manchak tries to bring in a more local, observer-focused perspective. Imagine a freely falling observer, right? They have a watch, they're keeping track of time. Now, space-time is not effectively complete if there's some specific reading on their watch that they never reach, even though locally there's nothing stopping them from getting there.
Interesting. So it's not about the math of the path itself, but what an observer could, in principle, experience. So a singularity is a place where experience itself breaks down. Is that kind of a valid way to think about it?
It's one way to interpret it. And what's exciting for a philosopher is that this idea of effective completeness sits between those purely mathematical definitions like geodesic completeness, which we know is too strong, and this really weak condition of just being extendable. It's a new approach, but there's still a lot of open questions, like can we prove significant theorems using this idea? Can it really help us understand the philosophical questions we're dealing with?
Okay, so even defining something as seemingly fundamental as a singularity is still up for debate. Nobody's fully satisfied. And that immediately throws up a whole bunch of philosophical questions, right?
Oh yeah, like how much should the explanatory power of a definition matter? How do our preconceived notions about space, time, and existence influence how we define a singularity? And really, what does it even mean for something, a physical entity or even space-time itself, to exist under these super extreme conditions? And maybe the biggest question of all, what's the status of our mathematical models? Are they truly representing reality, or are they just useful tools for organizing what we know?
Okay, that's enough to keep a philosopher busy for a lifetime. So let's shift gears a bit. We've been talking about singularities as these points where things break down, but there's another way to think about them as boundaries or missing points in space-time. This is like the classic image of a hole in the fabric of the universe, a place where things literally just cease to be.
Yeah, it's a powerful image. And there's this real desire, a real urge to characterize singularities as actual spatiotemporal places.
Yeah.
Because if we could do that, then maybe we could actually analyze the structure of space-time, like right up close to the singularity itself, instead of just looking at the paths leading up to it.
I get it. It's like, if there's a hole, can we go and examine the edges of the hole?
Exactly. But here's the kicker. The mathematical structures we use to describe space-time, these things called manifolds, they often appear to be perfectly well-behaved, complete, with no holes. It's like trying to find a missing point on a perfectly smooth, infinite plane.
So the math doesn't seem to match the intuitive picture of a hole.
Not quite. Think about a star collapsing into a black hole. Everything that crosses the event horizon, well, according to classical theory, it's doomed to hit that central singularity in a finite amount of time. It feels like those paths are ending at something, at a point that's missing from the space-time. But the mathematical manifold we use to describe that space-time, it's complete. There's no hole to patch.
That's wild.
Yeah, and it's not just black holes. The Big Bang is another good example. All the paths going back in time, they seem to converge on the Big Bang. We talk about time zero, but that's just a label. There's no actual point, no moment that corresponds to the Big Bang, in the same way that there are moments within the subsequent evolution of the universe. The way we model the universe mathematically, there's no before the Big Bang. That's not part of the picture.
Okay, that's really messing with my brain. So have physicists and philosophers dealt with this clash between our intuition and the math?
Oh yeah, they've had all sorts of reactions. Some, like Clark, seem comfortable with these boundaries at infinity, accepting that maybe our intuition needs to be revised. Others, like Wald, are more hopeful, thinking we might find a better way to construct boundaries that match our intuition. Some, like Joshi, kind of sidestep the whole issue. And then you have folks like Guro and Curiel, who argue that maybe this whole desire for boundaries is misguided.
Okay, so lots of different opinions. But if these mathematical models are complete without these missing points, why have so many brilliant physicists spent so much time trying to construct boundary descriptions? What's the motivation?
That is a great question, a deep one. It could be that they're driven by a desire for mathematical elegance, for a more local description of these phenomena, but our source suggests there might be a deeper, almost metaphysical urge at play, like a need to have these singularities be things at places.
A need for things to exist in a way that we're comfortable with.
Exactly. We crave ontological clarity even when the physics itself seems to resist it. And even if we could construct these boundaries, it would just raise more questions. Like, what kind of theoretical entities would these missing points be? How would they work within our physics? What would it even mean for them to exist?
Heavy stuff. Okay, let's move on to the third way of thinking about singularities, through the lens of curvature. The idea is that at a singularity, the very geometry of space-time becomes infinitely warped, totally messed up.
Right. The intuition here is that if paths are incomplete, if space-time seems to have these edges, it must be because the geometry itself is going haywire. And what better way for geometry to go wrong than for the curvature to become infinite? And that's what our math seems to show, right? And the places we associate with black hole and Big Bang singularities, local measures of curvature tend to blow up to infinity.
Yeah, makes sense. Extreme gravity, extreme curvature. What's the problem with that?
The problem is that, as our source carefully points out, none of our current definitions of curvature pathology are actually both necessary and sufficient for pathing completeness. You can have spacetimes where curvature goes to infinity, but paths are perfectly fine and vice versa. It's not a one-to-one relationship.
So even if the math says curvature goes to infinity, it doesn't mean things have to end there.
Right. And then there's the issue of how we connect this mathematical concept of curvature to something we can actually measure, something physical, like tidal forces, the way gravity stretches and squeezes things differently at different points. But the way these forces manifest depends on the object you're using to probe them. So is the curvature pathology really a property of the spacetime itself, or is it relative to how we're measuring it? What even counts as a fundamental measure of curvature in general relativity?
Big questions for philosophers of science, right? What is a real objective property if it depends on how you measure it?
Exactly. Our source really emphasizes the need for more philosophical work on these foundational issues, the nature of physical quantities and observables in general relativity. It even suggests that maybe our current way of defining curvature pathology isn't the best way to capture what's going wrong at singularities. Maybe it's not really a localizable property of space-time itself.
So maybe we're looking for the wrong kind of breakdown.
It's possible. But there's a special class of singularities called conformal singularities, where the curvature pathology is specifically confined to the conformal part of the curvature. This part is all about angles and the structure of the light cone. And in these cases, it seems like we can actually attach a meaningful boundary. Many physicists think that all the essential information about gravity is encoded in this conformal structure.
Okay, so we've got these classic ideas about singularities, incomplete paths, missing points, curvature going crazy. But the universe always has surprises, right? These new, weird types of singularities, the so-called non-standard singularities. What are those about?
Yeah, those are wild. In 2004, physicists discovered these things called sudden singularities. In certain cosmological models, you can have situations where the rate of change of the expansion of the universe, or a parameter called the Hubble parameter, becomes infinite, but the expansion factor, or the Hubble parameter itself, remains finite.
So it's not that the universe is becoming infinitely big or infinitely small, but the rate at which it's changing is going bonkers.
Exactly. And what's interesting for a philosopher is that these sudden singularities are structurally very different from the classic types, but we still call them singularities. So what does that mean for our scientific language? When we use the same term for different things, what's the justification? What are the underlying similarities that allow us to group them together?
It's like our concept of singularity is being stretched to accommodate all these new weird behaviors, and then there's the big rip, right? Another one
Yeah.
of these cosmic calamities.
Oh yeah, the big rip. Imagine the expansion of the universe accelerating faster and faster, eventually becoming so strong that it overcomes all other forces, tearing apart space-time itself in a finite amount of time. So instead of collapsing to a point, the universe just explodes outwards, its volume going to infinity. And our usual ways of characterizing singularities based on incomplete paths, they don't really work for the Big Rip, even though there are still incomplete paths and messed up curvature involved.
So the universe could end not with a bang or a whimper, but with a rip. That's dramatic.
It's one possibility, according to our current understanding. And all these different types of singularities force us to ask, like, are these things actually real? Are they features of the universe, or are they just problems with our theories?
The million-dollar question. So general relativity, and especially those big singularity theorems, they seem to say, yeah, singularities are real. They point to the Big Bang, black holes, and maybe even a big crunch or a big rip in the future. So if the math is saying they're real, why are some people still resistant to the idea?
A bunch of reasons, many of them very philosophical. Some people just find the whole concept of a singularity a place where physics breaks down, too much to swallow. Others say, look, if our theory is predicting these crazy things, maybe it's a sign that the theory itself is limited. And then there are those who just accept it. They say, okay, the theory says singularities are real, so they must be real.
A real tug of war between our theories and our intuitions. So what do we do?
Well, one response is to say, we need a better definition, a definition that's precise, rigorous, and works for all types of singularities. The hope is that a better definition will help us answer those big questions. Are they real, or are they just mathematical ghosts? Another response is to say, look, maybe we don't need a perfect definition. General relativity is still incredibly useful, even if we don't have a perfect grasp of what's happening at singularities. Let's just focus on the physics.
It's kind of like our earlier discussion about locating singularities, about treating them as places. You mentioned this connection to Aristotelian substantivalism, right? The idea that space and time are fundamental things in which objects exist.
Yeah, that's right. We have this deep-seated need to locate things, to say that they exist somewhere. But that might be the wrong way to think about singularities. Lots of things in physics, like the overall shape of space or the specific way we measure distances, they're not localized in that sense. So why should we demand that singularities be localizable? It's a really interesting philosophical puzzle that's often overlooked.
Maybe we're imposing our everyday way of thinking about objects onto something that's fundamentally different.
Could be. And, in other areas of science, when a theory starts predicting really weird things, it's often a sign that the theory has reached its limits. Like in Newtonian gravity, if you have a point particle, its gravitational potential becomes infinite. But we don't actually believe that's a real thing. We know that's a sign that Newtonian gravity isn't the whole story. Maybe singularities in general relativity are similar.
So maybe they're just placeholders for a better, more complete theory of gravity, maybe one that incorporates quantum mechanics?
A lot of physicists hope so. They think that quantum gravity will somehow smooth out those singularities, make them less, well, singular. But some recent work has shown that it might not be that simple. Singularities might be more stubborn than we thought.
That's kind of scary. Okay, so singularities are these weird, ill-defined things, and we're not even sure if they're real. Let's move on to black holes. They're also predicted by general relativity. They often have singularities at their centers, but they also have these more well-defined properties, like the event horizon. So beyond just being regions of no escape, what's philosophically interesting about black holes?
Well, the popular image of a black hole as a giant cosmic vacuum cleaner isn't entirely wrong. They do form when massive objects collapse under their own gravity, becoming so dense that nothing, not even light, can escape. And that's where the event horizon comes in.
Right, the event horizon, the point of no return. So what's so philosophically interesting about that?
Think of it like this. The event horizon is the boundary of a region in space-time where it's impossible to send any signal, any information, out to an observer far away. Anything that crosses that boundary is cut off from the rest of the universe. It's trapped, and according to classical theory, it's doomed to hit the singularity at the center.
Okay, that's terrifying. But what about an observer who's falling into a black hole? I've heard all this weird stuff about time dilation.
Right, so imagine you're watching someone fall into a black hole from a safe distance. As they get closer and closer to the event horizon, they'll appear to slow down. Their time will seem to stretch out infinitely, and from your perspective, they'll never actually cross the horizon. Their image will just get redder and fainter as they approach it.
So they're frozen in time at the edge of the abyss. Creepy.
Yeah, but here's the twist. For the person actually falling in, it's a completely different story. They wouldn't notice anything special at the event horizon. They wouldn't feel any special forces, no sudden change in their surroundings.
So it's not like hitting a wall or anything.
Nope. The event horizon is a global property of spacetime, not a local barrier. It's defined by the overall distribution of mass and energy, and its location today actually depends on what will fall into the black hole in the future.
Wait, so the black hole knows what's going to happen in the future? That's messing with my head.
Yeah, it's one of the strange and philosophically challenging aspects of general relativity. This prescient nature of the event horizon, the fact that it seems to depend on future events, is hard to reconcile with a strictly empiricist view of the world. You can't determine its presence through purely local measurements.
It's like the black hole is somehow aware of its future. That raises all sorts of questions about causality and time. So to properly define a black hole, we need to think about these global properties, this idea of being trapped within a region from which there's no escape. And once something falls in, it's gone, presumably crushed at the singularity. But the black hole itself, it only retains a few key properties, right? That's where the no-hair theorems come in.
Precisely. These theorems are remarkable. They say that once a black hole settles down, it's completely described by just three things: its mass, its spin, and its electric charge. That's it. All the other information about the matter that collapsed to form the black hole, it's lost to the outside world.
So if you take a star and collapse it into a black hole, and then take, I don't know, a bunch of old philosophy textbooks with the same mass, spin, and charge, and collapse them into a black hole, you wouldn't be able to tell the difference.
Not from the outside. And this simplicity extends even further. The topological censorship theorem says that the space-time around a black hole is topologically very simple. No wormholes, no weird time loops, at least outside the event horizon.
Wow. So these incredibly extreme objects also impose a kind of order on the space-time around them.
It's one of the fascinating things about them. And it raises all sorts of questions about the relationship between the topology of space-time, its overall shape, and its metrical structure, the way we measure distances. These are deep philosophical questions that haven't really been explored that much.
So much to think about. Now, the standard definition of a black hole with its global event horizon, it's really useful for theoretical work. But what about real black holes in the universe? They're not perfectly isolated systems, right?
You got it. Real black holes are messy. They're interacting with their surroundings. And that's where the concept of quasi-local black holes comes in.
Quasi-local, what does that mean?
So a physicist named Raymond Hayward proposed a more general definition of a black hole based on the idea of a trapping horizon. Instead of looking at the entire space-time, we just focus on the local behavior of light rays. Basically, a trapping horizon is a surface where ingoing light rays are converging and outgoing light rays are either also converging or momentarily parallel.
So it's like a local version of the event horizon.
In a way, yes, but what's cool about this definition is that it's locally measurable. An observer could, in principle, determine if they've crossed a trapping horizon. They wouldn't need to know the global structure of space-time.
That's pretty neat. And I remember our source mentioned something about it maybe being possible to escape from some quasi-local black holes.
Yeah, that's one of the intriguing possibilities. It challenges the whole nothing can escape idea that we associate with the global event horizon. It suggests that our standard picture of black holes might be too simplistic when we consider these more dynamic, realistic scenarios.
I like it when the universe throws us curveballs. So we've got all these different black hole definitions. Event horizons, trapping horizons, and a bunch of others used in different areas of physics. Why so many definitions for what we think of as the same object?
It's because the term black hole is used in so many different contexts, from classical general relativity to quantum gravity to astrophysics. And each of those areas has its own set of questions and priorities. So researchers often start by saying, okay, what are the key properties we care about? And then they look for a definition of a black hole that captures those properties. Sometimes they even come up with new definitions if the existing ones aren't quite right for the job.
It's like trying to define a black hole is almost as hard as defining a singularity.
In some ways, yes. It raises a lot of interesting questions about how we define things in science, especially when we're dealing with objects that are so extreme and hard to observe directly. Like, is the standard event horizon definition just an idealized picture that doesn't really apply to real black holes?
Yeah.
Are these other definitions attempts to capture the messiness of the real universe? How do we compare different definitions and decide which one is better? And do we even need a single all-encompassing definition of a black hole? Or is it okay to have different definitions for different purposes?
Yeah, it's a real philosophical puzzle. So for the rest of our discussion, we're sticking with the standard global event horizon definition, right?
Yeah, that one's probably the most useful for our purposes.
Makes sense. So as we wrap up this deep dive, we've explored this incredibly strange and fascinating world of space-time singularities and black holes. We've seen how hard it is to even define these things, how much debate there is about whether they're real or just mathematical artifacts, and how they challenge our most basic intuitions about space, time, and existence. It's clear that there's still so much we don't know, and this is an area where physics and philosophy have to work together to make progress.
Absolutely. For philosophers, these topics are a gold mine. They force us to think about the nature of science, the limits of our knowledge, and what it even means for something to exist.
And they leave us with this really provocative question, don't they? Given how much trouble we've had trying to understand singularities and black holes, what does that say about our current ways of thinking about the universe? Maybe we need to develop entirely new conceptual tools, new ways of approaching these questions to really make sense of these most fundamental aspects of reality.
It's something to think about.
It is. Thanks for joining us on this deep dive.
Absolutely. Until next time.